Okay, now every reversible system, and reversible means equilibrium. Okay, so when we see those double arrows, we're talking about a reversible chemical reaction. So every reversible system has its own position of equilibrium under a given set of conditions. Okay, we're going to see if we change the temperature, that's going to affect the equilibrium, depending on whether it's an exothermic or endothermic reaction. If it involves gases, we'll find that changing the pressure will also affect the equilibrium. Okay, and so we'll explore all of those things later on. So the ratio of the products to unreacted reactants, in other words, products over reactants, for any reversible system remains constant at equilibrium. As long as the conditions of pressure and temperature remain constant, that is true. So the numerical value of this ratio is what we call the equilibrium constant, or capital K. So that's our equilibrium constant. So here we go. Here's our generic reaction, right? So we have reactants A and B going to products C and D, and they're raised to the lowercase coefficients of A, B, C, and D. So the equilibrium constant expression, we're going to call capital K. Now the subscript C here means that it is just a generic equilibrium constant. Usually we don't even include C. We would just call this capital K. Now we're going to find out that there are other subscripts like Ka. That's the acid equilibrium constant. Kb, the base equilibrium constant. There's going to be a Ksp, which is for solubility. There's going to be a Kf, which is for the formation of complex ions. There's a Kd, which is the decomposition of complex ions. So there's going to be a lot of different K values. There's going to be a Kp, which deals with gases. Okay, so Kc is just the generic way of saying it. Again, usually we don't even put the C, we just call it capital K. And you can see it's the concentration of the products, our C and D, each raised to the coefficient in the balanced chemical equation, divided by our reactants A and B, again, each raised to the coefficient in the balanced chemical equation. And these are always given in terms of molarity, right? So the square brackets are going to be moles per liter. So there it is. Okay. Now later on, we're going to find out that not all of the reactants and products are necessarily going to be in your equilibrium constant. We're only going to put either aqueous solutions or gases in the equilibrium constant. Pure solids and pure liquids are not going to appear in the equilibrium constant. I'll talk about why later on. Okay. Okay, so again, we got to determine the equilibrium constant experimentally. There's no other way to do it. We just got to do the reaction once. But once we determine that K value at a given temperature and pressure, it's never going to change. In fact, there's tables where you could find literally hundreds of thousands of these values. So hundreds of thousands of chemical reactions have already been studied and the K value is determined. Okay. And we've already seen that if we have a large Kc value greater than 1, and if it's much, much greater than 1, basically it's going, equilibrium is established when basically everything goes to, okay? So equilibrium is established when everything goes to product. If it's small, again, like our weak electrolytes, that means that basically everything is going to remain as unreacted reactants when equilibrium is established. Very little products are actually going to be formed. And again, we're going to be able to quantify all of this here shortly. Okay, so we know that soluble salts are strong electrolytes. And again, soluble only means that it dissolves in water. It doesn't mean strong electrolyte unless we're talking about salts, right? Soluble salts are strong electrolytes. And we normally don't give them an equilibrium constant because we basically assume that their K values are extremely large and it goes mainly to products, right? Sodium chloride is a prime example of that. When we put sodium chloride in water, we assume that it 100%, so we draw a single arrow, we assume that it goes completely to the sodium and the chloride ions. The reality is that there is an equilibrium. It's just that the K value is very, very large. So an ionic compound can be classified as soluble when its K value is greater than 1. Now, this is fuzzy. This is not a set value, okay? Sometimes we call, for example, we call calcium hydroxide a strong base. The reality is the K value for calcium hydroxide is about 10 to the negative 1 to 2, 10 to the negative 2. But it's still very close to 1 that we call calcium hydroxide a strong base. So again, this thing is fuzzy. But usually when we have a salt and its solubility, its equilibrium constant is greater than 1, we generally say it's a strong electrolyte. So that's where we get this idea of strong electrolytes and weak electrolytes. It's based on the equilibrium constant value. Now we can actually calculate what's called the KSP. So again, this is the solubility product constant. So this is the equilibrium constant for soluble salts. If we just looked at a slide where we showed that, you know, a certain number of grams of, I think we established it was 36 grams of salt will dissolve in 100 milliliters of water, okay? If we just use that very simple idea, we could actually calculate a KSP value for the solubility of sodium chloride. So this reaction here has a value of 38. Now I say approximately because any of you who are going to go further, like get a chemistry minor, does anybody here plan on getting a chemistry minor? Nobody? Yeah, okay, one person. Okay, so you're going to have to take what's called analytical chemistry. And we're going to find out that it's going to be very complicated to actually calculate the real KSP of sodium chloride. Because I'm not telling you the whole truth. I can't tell you the whole truth at this time or I'd blow your mind, okay? These systems are really very complicated. So we're going to, basically what chemistry is we start off with Gen Chem and kind of tell you everything and then really, really, really go into detail of how these things work as we go along. So just keep in mind that we can't simply take what mass dissolved in water and say for sure that is going to be, we're going to have this value, K equals 38, to calculate the concentrations of these. We'll find out that it's much more difficult than that. It's also going to involve something called the activity coefficient, okay? And all that basically talks about is that if you have ions in water, the more ions you have, the more soluble all ionic compounds are. So it also involves that activity coefficient, okay? So again, you'll learn any of that if you go on to analytical chemistry. Okay, so let's use the Haber process again to explore this equilibrium constant. So here's the equilibrium constant expression. You're going to hear this a lot. So when I say equilibrium constant expression, again, we're just saying that K is equal to the concentration of the products raised to its coefficient in a balanced chemical equation, divided by the reactants, each raised to the coefficient in the balanced chemical equation. So nitrogen raised to the first, and then the hydrogen raised to the third. And so there is the equilibrium constant expression. If you're an engineer, they call this the law of mass action. So the law of mass action is exactly the same thing as what a chemist calls the equilibrium constant expression. It's just basically saying that once the equilibrium is reached, the masses of the reactants and products no longer change. They remain constant. So that's all the law of mass action is saying. It talks about the masses instead of the moles. Okay? Okay, so there is our equilibrium constant expression then for the Haber process. And if we reversed the process, right, now we'd put the products, again, each raised to the coefficient, divided by the reactants raised to the coefficient, and that would look like this. I put the prime here just because this is for the reverse reaction. My point here is the relationship between these two reactions and the K value. The K value for the reverse reaction is just the inverse of that original equilibrium constant. So K prime is just equal to 1 over K. We're going to be manipulating these equations later on. We're going to be adding them up again. Okay. And so whenever we have to flip a chemical reaction, we just take the inverse of that equilibrium constant. Okay. So again, we got to determine them experimentally. So let's consider another reaction. This is a reaction. It's actually the reverse reaction. Usually what we do is we take methane and we react it with steam at very high temperatures, and we form carbon monoxide and hydrogen. So this is how we produce most of our hydrogen today, is we actually react the methane to form hydrogen gas. So, but this is the opposite of that. This is where we have carbon monoxide reacting with hydrogen to form methane and water vapor. And let's say we have a 10-liter vessel, and it contains and it contains 2 moles of CO, 3 moles of H2, and this results in initial concentrations of 0.2 molar. So all I did was take the 2 moles divided by 10 liters, right? So that's the molar concentration, so 0.2 molar, and then the 3 moles divided by 10 would be 0.3 molar. So those are the initial concentrations of my CO and my H2, okay? We're assuming, again, we had a clean reaction vessel, so there was no product, so no methane or water. Once equilibrium is reached, these are now the new values of the reactants and products. So once we do this chemical reaction, we've measured the concentration of the reactants and products. We can now plug these into the equilibrium constant expression for this reaction, right? So K is going to be equal to the concentration of methane raised to the first times the concentration of water raised to the first, divided by the concentration of CO to the first, divided by the concentration of hydrogen raised to the third, right? So that would be our equilibrium constant expression. And now we're going to plug in our equilibrium values. So we'll plug them into the expression, do our math. Now, note that there's no units for this number. So unlike rate constants, where we always had to figure out the units, we don't need to do that for equilibrium constants, because we know that the answers are always going to be in terms of molarity. So even though this moles canceled that molar and this molar cancels one of these 3, so really this would have units of per molar squared. But again, for these equilibrium constants, we don't use units because we know that everything's always in molarity. Okay?
Wait, so for those values, did you find those by doing an ICE table?
No, we did the experiment. We went into the lab. We started off with our initial amounts. We put it in our reaction system. We waited for the system to come to equilibrium. So basically all we did is we just keep measuring the concentration of, let's say, carbon monoxide. Once the concentration of carbon monoxide stops changing, we know that we've reached equilibrium. So then we experimentally measured all of these equilibrium concentrations for both our reactants and products. Okay, so we did this experiment. And then we plugged those in and we came up with our equilibrium constant of 3.93. Okay, so this is, we had to do the experiment originally, but now that we know this equilibrium constant under these particular conditions, this number is never going to change. Here we can show this. Let's do a second experiment. So again, we're going to go into the lab, we're going to do a second experiment. Okay, this time, so again, this is just talking about the law of mass action and the fact that this doesn't change anymore. Okay, so this time let's start with the just products, 0.1 mole of each of the products and no reactants. Again, we put it in the reaction vessel at the same conditions that we did the last experiment for, and at equilibrium, we end up with these values here. Now, again, I'll plug that into the equilibrium constant expression, right, with our equilibrium concentrations, plug it into my calculator, and again, I come up with the exact same number, 3.93. So again, as long as you're at the same temperature and pressure, if gases are involved, then you're always going to have the same equilibrium constant. Any questions with that? Okay, so that's how we determine them experimentally. We literally go into the lab, we put our reactants in, wait till the concentrations quit changing, measure the concentration of all the reactants and products. And actually, a lot of times you're going to see we don't have to measure all of them. We can measure one of them because we know that they're all related through the coefficients in the balanced chemical equation. Okay. Okay. So again, no matter where you start, you're always going to reach the same equilibrium. Now, we can combine equilibrium reactions of known reactions with known equilibrium constants to figure out some new overall reaction and then calculate its equilibrium constant from those other reactions that we combine together. So we've already seen that if we flip a reaction, all we do is take the inverse of the equilibrium constant, okay? So we've seen that, right? If we reverse the reaction, we just invert the value of K. We take its inverse. If we multiply each of the coefficients in the equation by some factor, let's say 2, well, we're going to raise the equilibrium constant to that same power, right? Because remember, those coefficients end up being powers. We raise each of the concentration of the products to a given power, which is that coefficient. So if we multiply the coefficients by any value, we got to raise it to that same power. If we divide each coefficient, well, we're going to have to take the square, whether it's a square root, cube root. Now, I don't like dealing with that. So if I multiply by 1/2, which is the same as dividing by 2, right? I'm just going to raise it to the 1/2 instead of having to worry about all these roots, okay? And then finally, you're going to combine, you're simply going to add the individual equations together and then multiply, right? You want the product, you're going to multiply all the equilibrium constants together. So this is different than what we did with the rate constants, as you recall, okay? Okay, so let's try an example. Let's say I want to know the equilibrium constant for the reaction between nitrous oxide and oxygen to form 2 nitric oxide molecules. But for whatever reason, I can't perform this experiment and determine the equilibrium concentrations. But I do know of a couple of other examples. I know the equilibrium constant for nitrogen reacting with oxygen to produce nitric oxide is 4.1 times 10 to the negative 31. Now this is 10 to the negative 31, right? Which means that almost no NO is formed from these reactants under these conditions. And then 2 nitrogens reacting with 1 oxygen to form nitrous oxide, 5.8 times 10 to the negative 36. So even less of this is formed from the initial reactants under these conditions. Okay, so that's again, very, very small K values means very, very few products were formed. Okay, now I need to manipulate these equations so that when I add them together, I get this. So I'm going to look for something that is unique to this, the original equation, and to each one of these. So the nitrogen, well, first off, it doesn't even appear in this equation, and it's not unique because it appears in more than one equation. The oxygen appears in all 3 equations. Hopefully that'll just work itself out. But I have nitric oxide, which only appears in this equation and this equation. So I'm going to focus on this. And well, what I see is that it already is a product, and it's a product here. There's already 2 here, and there's 2 here. So I don't have to do anything to this equation. Now let's look at this equation. Well, again, we established there's not even any nitrogen. Oxygen's in too many of them, but the nitrous oxide is only in one of the reactions and in the overall reaction that we're looking for. Problem here is it's backwards. I need to flip this reaction, right? I need to get this product into the reactant, so I need to flip the reaction, okay? So, and again, this is what we're trying to get, right? We're trying to add these together to get this. So first, I'm going to flip this reaction, okay? This -1 should be a superscript. This should be a superscript. This should be raised to the -1 this time, okay? And so 2 to the -1, this is still incorrect. Okay, this again should be raised to the -1. Okay. So again, it's just the inverse. We flip the reaction now. Now we got them as both reactants, and we flip the reaction. But again, I only need 1, and there's 2. So I'm going to multiply each coefficient by 1/2. And when I do that, I got to raise this entire thing to the 1/2. Okay? So whatever I do, whatever I multiply the coefficients by, I got to raise the equilibrium constant to that same value. So now I can just add them together. Okay, so I can see that the N2 cancels. The NO2 comes straight down. I have 1 O2 on this side, a half O2 on this side. So this half is going to cancel that 1. Okay, so that's going to leave me with 1/2 O2. Then the only thing left, these are both canceled, so the only thing left are these 2 NOs, and they come down. Okay, any questions so far? Okay, then we just need to multiply together these equilibrium constants. Okay, and that's going to give us a value of 1.7 times 10 to the -13. So basically, we can see that nitrous oxide reacts with oxygen to form 2NO. It has a much more products, right? These were originally like 10 to the -31, 10 to the -36. Still, we're forming very, very little of this, but it's still much, much greater. Now I'm going to talk about orders of magnitude. Does everybody understand what an order of magnitude is? So an order of magnitude is when you raise 10 to a power. So if I say it's 2 orders of magnitude, I'm talking about 10 to the 2. Okay. So the difference between 10 to the -31 and 13 is 18 orders of magnitude. It's a huge number. So that'd be 10 to the 18 difference between these 2 reactions. Okay, so is everybody comfortable then at being able to determine new equilibrium constants from given reactions? Okay, let's start discussing gas phase equilibria. So now we're going to introduce a new equilibrium constant called Kp. And so it's more convenient oftentimes to write the equilibrium constant in terms of pressures, because that's how you're measuring gas reactions. You're just using a simple pressure gauge. Okay, so We can relate the Kc value, the equilibrium constant in terms of molar concentrations, to Kp by using the ideal gas law. Well, we know that molarity is just the number of moles divided by the volume, right? So that's the molarity that we're talking about there. So I'm going to say that molarity is capital M. So here's an example, right? We have this gas cylinder, and we have a movable piston, and then we're measuring the pressure. Now, we know that we could also think of this in terms of molarity, right? So it's the number of moles of gas divided by the volume that it's in. So if I push down and I squeeze the gas, I reduce the volume, what happens to the molarity? Michael, what will happen to the molarity if I push down on this cylinder and reduce the volume?
It's going to go down. Wait, it's going to go up.
It's going to go up, right? Because now I have the same number of molecules, but I now have a smaller volume. And the same thing with the pressure, right? The pressure is going to go up because now, instead of this molecule having to travel this entire distance to hit the container, it's only going to travel half the distance. So now it's striking the walls of the container twice as often. And so the pressure would be double if I halved it, right? So if I half it, in this case, it's a lot more than half. But again, the pressure is going to go up and the molarity is going to go up. So we can see that pressure and molarity are directly related to one another. Okay. So let's take, for example, again, the carbon monoxide reacting with hydrogen to form methane and water vapor. Okay. We could put this in terms of pressures. Okay. Now we're going to do our pressures all the time in atmospheres. The reality is, if you are working with Kp values, usually you put them in bar. But bar isn't even a pressure unit that we've talked about. Okay, we've talked about atmospheres, millimeters of mercury, torr, kilopascal, Pascal. But bar is just another way of measuring atmospheric pressure. But we're going to do ours in atmospheres. Okay, so again, you can see it's just the partial pressures of the products, each raised to the coefficient in the balanced chemical equation, divided by the partial pressure of the reactants. Again, each raised to the coefficient in the balanced chemical equation. So these are now partial pressures of the gases in atmospheres, each raised to the coefficients in the balanced chemical equation. Now, I know that molarity equals this, right? Just rearranged from the last slide. So if I plug that in and do some simple algebra, I can find the relationship between Kc, so the equilibrium constant in terms of molarity, and Kp, the equilibrium constant in terms of atmosphere, partial pressures of the reactants and products. So this is just RT. R being, since we're dealing with atmospheres, right, this is going to be the R value of 0.082058 atmosphere per liter per Kelvin per mole. The temperature is going to be the absolute temperature, so the temperature in Kelvin. And then this del N is actually the change in moles of gas, right? So it's going to be gaseous, moles of gaseous products minus moles of gaseous reactants. So it's only going to involve moles of gas. Okay, it won't, no solids, no liquids, no aqueous species, just gases. And again, R is just that 0.08. I'm going to add that to this slide, 39. Okay. Okay, so let's try an example. Let's say the equilibrium constant, now this is Kc, for the gas phase reaction of sulfur dioxide reacting with oxygen at 1,000 degrees Celsius to produce sulfur trioxide, has a Kc value of 2.8 times 10 to the 2, so 280. So the products are favored in this reaction. We want to calculate the Kp. Well, again, we know the relationship between Kp and Kc is that Kp is equal to Kc times the quantity of RT raised to the del N. what is, without looking at your notes, what is the del N value of this? Hannah, what's the del N value?
It'd be the products minus the reactants. So 2 minus 2 plus 1, so -1.
Yeah, so del N is going to be -1, right? So again, we're looking for this del N. We already know the value of R. T is going to be 1,273.15 Kelvin, right? This has got to be in Kelvin. So we got to add 273.15 to this. And then del N, well, again, these are all gases. You got to make sure you look at these phase labels. These are all gases. So we have 2 moles of product, and we have 1, 2, 3 moles of reactant. So it's going to be 2 minus 3, and that's going to be -1. So now we can plug it in. We know that R is our 0.082058 atmosphere liter per Kelvin per mole. We've already established del N is -1. And again, we're going to convert the temperature to the absolute scale. So we're going to add 273.15 to that. Now we can plug all this in with our value of 280 for Kc. And that is going to give us a value of 2.7. So again, we could go back and forth between Kp and Kc by simply using this expression right here. Any questions with any of that good stuff? Okay, now let's talk about heterogeneous equilibria. So again, we have things that are in more than one phase. The equilibrium of a heterogeneous system is unaffected by the amounts of pure solids and pure liquids, as long as some of them are present. Now, the reason being is that if it's a pure solid or pure liquid, there's so much of them compared to what would be in the gas phase. Again, the gas phase has much lower concentrations because there's a huge distance between each of the molecules. Same thing with aqueous solutions. We're generally dealing with dilute aqueous reactions, so there's very few chemicals in the aqueous solution. So if you have a pure solid or a pure liquid, basically its molarity is unchanging. Just again, because there's so much, it's in such excess compared to the gas or the aqueous solution that we just ignore it. Are there situations in which we can't? Yes, of course, but we're not going to deal with them. They become very complicated very quickly, so we're not going to deal with them. But we're going to see how sometimes those pure liquids and pure solids actually get incorporated into the equilibrium constants itself, since that value remains constant. We'll deal with that actually in the upcoming chapter, okay? In chapter 16, when we start talking about weak acids and bases and acid-base reactions and solubility and all of that stuff, okay? Okay, so again, we basically consider their concentrations to be 1, but like I said, it's a bit more complicated than that. It actually becomes part of the equilibrium constant itself. Okay, so let's write the equilibrium constant reaction for this heterogeneous reaction. So again, it's going to be our products. And again, the only thing that appears in the equilibrium constant expression are gases and aqueous solutions. So these are both gases. So it'll be the concentration of CO2 raised to the first times the concentration of H2 raised to the second. We're going to divide that by our products, but this time there's a solid. And again, pure solids and liquids don't appear, so that won't appear. So we're just going to divide it by the concentration of H2O raised to the second. Okay, again, notice that pure solids and liquids do not appear in the equilibrium constant expression. Watch out for those phase labels. Okay, and in terms of Kp, well, since these are all gases, it'd just be the partial pressures, again, each raised to the coefficient in the balanced chemical equation. Okay. Okay, any questions with any of this good stuff? Okay, now, if K is greater than 1,000, basically the whole reaction went to products. There is almost no reactants left whatsoever. Again, very large means mainly products. Very, 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 very few reactants left over. If K is very small, so less than 1/1000th, then basically it mainly remained reactants, and there's barely any products formed at all. And of course, we've seen if Kc is in range basically of 10 to the -3 to 10 to the 3, the equilibrium mixture contains a measurable amount of both reactants and products. Okay, I shouldn't use the term measurable amount, a considerable amount of both reactants and products. Okay. Okay, so let's start with number 4. It simply says write the equilibrium constant expression for the following reaction. And again, the equilibrium constant expression is just capital K, which is the equilibrium. And that's going to equal what? Hannah, what's this going to equal?
The concentration of the products or the concentration of the reactants. Oh, word.
Okay, be more specific.
So using the chemicals, it'd be the concentration of NO to the 4th times the concentration of H2O to the 6th over the concentration of NH3 to the 4th and multiplied by O2 to the 5th.
Yep. So again, remember that the equilibrium constant is just going to be the products, each raised to the coefficients in the balanced chemical equation, divided by the concentration of the reactants, again, each raised to the coefficient in the balanced chemical equation. Taylor, how about the next one? What would you write?
I would do H2O to the power of 4.
Okay, so K equals?
Yeah, K equals, in the numerator, H2O to the power of 4, and then N2 to the power of 1.
Say it again.
H2O to the power of 4
Okay.
times N2 to the power of 1.
Okay. That's it?
Well, I think that's it because the Cr2O7 is a solid.
Yeah, absolutely. You're correct, right? Only gaseous and aqueous species appear in an equilibrium constant expression. Pure solids and pure liquids do not, right? So they're not going to appear in equilibrium constant expression. Okay, any questions about the equilibrium constant expression itself? It's fairly straightforward. Okay, let's try another. So this says nitrosyl bromide is formed from the reaction of nitric oxide and bromine in this following reaction. It says a 2-liter flask contains 0.0865 moles of NO and 0.0632 moles of Br2. Once the reaction reaches equilibrium, the flask contains 0.0623 moles of nitrosyl bromide. What is the composition of the equilibrium mixtures in terms of molar concentration? And then I want to know, what is the numerical value then of the equilibrium constant? So for these types of reactions, the best way to do this, to understand this, is to simply create an ICE table. Okay, and our ICE table is going to be the initial, the change, and then equilibrium. So it told us that, and also, by the way, all of these things are going to be in terms of molarities. So one of the first things I knew is just need to calculate the molarities. So for the NO, that was 0.0865 moles over our 2 liters. And so the molarity of that is going to be 0.04325 molar. And we got 3 sig figs. For the BR2, we have 0.0932 moles over 2 liters. And so that's going to be equal to 0.0466 molar. And then finally for the nitrosyl bromide, we have 0.0623 moles, again divided by the 2 liters. Since they're all in the same reaction vessel, they're all going to have the same volume. That's always going to be true. Okay. So now we can set up the ice table. So it says initially it contains the nitric oxide and the bromine. So that was these concentrations here. So initially we had 0.04325 molar the nitric oxide and 0.0466 molar of the bromine. Okay. And again, we're always going to assume that we have a empty reaction vessel. Okay, and it is going to be 0. So again, it's a clean reaction vessel. The change, well, we're always going to lose the reactants and gain the products. So the change is going to be, well, we're going to lose 2 of the nitric oxide. So we're always going to put this in terms of X, Y, or Z. So we're going to lose 2. So that's going to be minus 2X. We're going to lose 1 of the bromines, so that'll be minus X. We're always going to gain the product, so we're going to gain 2 of the nitrosyl bromide, so that'll be plus 2X. At equilibrium, it's always the same. We're just going to add the initial and the change together. So that's going to be 0.04325 minus 2X, 0.0466 minus X, and 0 plus 2X is just 2X. Now, for the first part of this question, it says, what is the composition of the equilibrium mixture in terms of molar concentrations? Well, that we could do right now because we know that it tells us here the flask contains this, which we determined was 0.03115 molar of nitrosyl bromide once it reached equilibrium. So that means this value here is actually equal to this value that we calculated for the nitrosyl bromide. Okay. So then to get X, we're just going to take that number and divide it by 2. And so that's going to give me a value then of wait a minute, I did something funky here. Oh, there we go. Okay, it's 0.015575 molar, 3 sig figs. So that's X. So then the equilibrium concentration then, right? This is just going to be 0.04325, that was to the 2 molar minus 2 times the 0.015575 molar. And that would give us a value then of 0.0121 molar. So that means the equilibrium concentration of NO then was 0.0121 molar. We'll do a similar thing for this guy here, right? So this guy here is going to be 0.0466 molar minus the 0.015575 molar. That's going to give us a value of 0.031025 molar. This is 1, 2, 3, 4 passed, 1, 2, 3, 4 passed, so 1, 2, 3, 4 passed. And so that means that our bromine at equilibrium is going to be 0.0310 molar. Okay. And then, well, we already know the concentration of the nitrosyl bromide that was actually given to us. So the nitrosyl bromide then, concentration at equilibrium is just 0.0312 molar to the correct rounding in sig figs. Okay, any questions about that? Everybody good? Okay. The second part says, what's the value of Kc? So, Leah, how am I going to calculate Kc for this reaction?
Hold on. I was still writing. Was Kc? That's the constant for. Let's see. Constant of the concentration. You can use the equation for the relationship between Kp and Kc. That one.
Okay, for that I'd need Kp. Did they give us Kp?
No. No.
So how am I going to get Kc then? Anybody help her?
Just do the same thing we did for the last question and just plug in the concentrations.
Okay, so in other words, write the equilibrium constant expression. So Leah, what is the equilibrium constant expression for this reaction?
That's going to be K equals, like bracket, NOBR raised to the second power.
Okay.
Quantity divided by, let's see, you got NO also raised to second power, and then just BR, 2.
Right, raised to the first since there's a 1 in
Yeah.
the coefficient. Okay, now what?
Well, now I would think that you would plug in the values that we got in molarity.
What values?
The
initial ones?
No. Well, the molar concentrations. Is that what?
At equilibrium.
Yes.
Right? So that's the important thing, right? So this K are these concentrations at equilibrium. So
Yes.
I'll plug them in. I'm going to use the unrounded values. So that would have been the 0.03115 molar squared. Well, I'm going to ignore units, right? Because we know that we're going to ignore units for the K value because the concentrations are always given in molarities. Then the NO, which was 0.1. Wow, that's bad. Okay, 0.0121 squared, and then the 0.031025. And then you would plug that into your calculator and you get 213.61. We have, this is 3 sig figs, 3 sig figs. This is 3 sig figs, so this will be 3. So your final answer would be 214. So the equilibrium constant for this reaction is 214. Okay. Keenan, if I ask you, does this reaction contain mostly at equilibrium? Does this reaction contain mostly reactants, mostly products, or is there substantial reactants and products?
At equilibrium.
At equilibrium.
Shouldn't there be substantial reactants and products?
Yeah, we see that actually, because we see
Yeah.
that in the values, right?
Yeah.
They're fairly close. We could have determined that without ever knowing these numbers by the equilibrium constant alone, right?
Yeah.
If this number is really big, greater than 1,000, then we're mainly going to have products. If this number is really small, less than 1/1000th, we're going to have mainly reactants. And if this value is between 1/1000th and 1,000, we're going to have substantial reactants and products once equilibrium is reached. Okay. Okay, does anybody have any questions about this problem?
Do we now have units in the
K
KC?
does not have units.
Okay.
Okay, the equilibrium concentrations all do, but remember, we ignore the units simply because we know that the concentrations are always going to be in molarity. So it just saves us a hassle of following the units. Okay. Okay, let's try another. So this says that sulfur trioxide forms from the reaction of sulfur dioxide and nitrogen dioxide, and then a byproduct is nitric oxide in this reaction. It wants us to obtain the equilibrium constant for this reaction given these other reactions here. So, Caitlin, how am I going to go about solving this? Is there an equation, a concept, some idea that I'm going to use? What do you think, Caitlin?
Give me 1 second. I can't remember it off the top of my head. Wouldn't you use the K constant equation with it? Or am I thinking of it wrong?
I think you're looking at it wrong. We're trying to find the K for this, right? So we're looking for the K for this, but the only information they gave us was this. Keenan, what do you think we're going to have to do?
So we're going to have to look at these equations, rearrange them, and then either multiply. I'm still like trying to figure it out, but then like multiply and divide it, and then we have to. So if we rearrange them, like flip them.
Why would you want to do stuff like that? What would be your end goal of rearranging these equations?
You need we need to eliminate the O2s because it's not in the original equation.
So you're trying to rearrange these and manipulate the coefficients in some way that when you add them together,
Yes.
get this reaction.
Yeah.
Absolutely, right? So that is the main goal of what we're doing. So if we have this reaction here, what would be the reactant of interest in this reaction here? In this first one? SO2, O2, or SO3?
The SO2.
Right. It would be the SO2 because it appears in our overall equation, and it only appears in one of these equations.
Yeah.
What about O2? Would you try it?
It appears in both of them, but it doesn't appear in the original.
Right. So it actually has two strikes against it, right? It's not in the original equation at all, so we don't really care about it. And on top of that, it's appearing in multiple equations down here. So we would ignore that. We could also look at the SO3, right? Because again, it only appears in one and it appears in our overall.
Yeah.
Okay. So do I need to flip this reaction?
I don't think we need to flip that one.
No, there's SO2 as a reactant, and this is a reactant. Do we need to do anything to the coefficients?
We need to take it by a half.
Okay, so we want to multiply each of these coefficients by a half. And when we do that, do we have to do anything to K?
Yeah, you multiply that by half as well.
No,
No?
not multiply,
Or divide it by half.
not divided by.
I'm confused.
Think about what happens here, right? So let's look at, forget this half right now.
Okay.
The equilibrium constant expression is going to be the products raised to the coefficients in the balanced chemical equation divided by the reactants
So
each raised.
you multiply that by half. Do you just take your coefficients and deal with the halves that way? So like you would,
Okay,
so
let
the
me,
SO3 2 would just be SO3. You would take away the 2.
okay, and how do we do that mathematically? So let me do this. So
Square
let me
root.
rewrite this. So this is now going to be SO2 gas plus 1/2 O2 gas is going to be in equilibrium with SO3 gas. So that K now looks like this. It's now going to be SO3 to the first over SO2 to the first over O2 to the 1/2. How do I go from that to that?
Square root.
The square root, which we could also say is just raising it to the 1/2, right?
Okay.
That is the same thing as saying the square root.
Okay.
Okay, so now remember, when you have an exponent raised to another exponent, we just multiply. So 2 times 1/2 is 1. 2 times 1/2 is 1. 1 times 1/2 is 1/2. So
Okay.
if we do this, we then raise this to the 1/2. So now this is going to be K1 is going to be equal to, I don't actually do it, so it's just 2.9 to the 1/2. Okay. Okay, does that make sense to everybody? Okay, let's see. Michael, what about this next one? What chemical?
We'll reverse it.
Okay, you want to revert. What chemicals first off are you going to look at?
The NO2 on the right side.
Okay, so you
And
can
to get
either
rid of
look
the
at the
oxygen.
NO2 or the NO, and then you're saying we need to flip it because this is a product, but we need it as a reactant. Okay, do we need to do anything to the coefficients?
Yeah, we gotta get rid of them.
And how do we do that?
Just do the same thing you did. Just multiply by 1/2.
Yes, we're just going to multiply by 1/2 again. So we're going to raise this to the 1/2, but we got to flip it as well. So that's what I'm going to do now. So I'm going to write, so I got NO2 in equilibrium with NO, right? I've already multiplied them by 1/2, and then plus 1/2 O2 gas. Now, I've already taken the square root or raised it to the 1/2. Did I have to do anything when I flipped it?
Don't you take the inverse of the rate constant then?
Absolutely. And how am I going to write that, Taylor?
You would just do 1 over 6.1 times 10 to the third.
Absolutely. So I'll show you 2 ways that I could do this, right? So it would actually be 1 over our 6.1 times 10 to the third, but we already have that to the half, right? So another way to express that is to say 6.1 times 10 to the third to the negative 1/2. You can actually plug it into your calculator that way, but make sure when you plug it in, you put parentheses around this guy so that you're getting the right answer. Again, you got to do your homework just so you're not making a bunch of stupid mistakes on the exam with your calculator. Okay? Okay, any questions so far about any of that? Okay, now if we did everything right, I should be able to add these 2 equations and get the original equation that I wanted. Well, I see I have a half of O2 on both sides. Now there's nothing else common, so I'm just going to bring down what I have, the SO2 gas, the NO2 gas, which would be in equilibrium with the SO3 gas, and the NO gas. Okay, so now I'm looking for this value. How am I going to determine that value? Eugenie, what am I going to do to get that value?
Products over reactions.
No. I mean, you're right, that it would be the concentration of the SO3 times the concentration of NO divided by the concentration of SO2 by the NO2, but I want the numerical value of K.
Do you add the first K and the second K?
Not add them.
Multiply?
Yep, we're going to multiply them, right? So we're going to take the 2.9 to the 1/2 times the 6.1 times 10 to the 3 to the -1/2. And we're going to plug that into our calculator. And again, when you're plugging this into your calculator, you got to be careful. I can say, now again, you could just use the square root button, but I just don't use it. So I'd have to type into my calculator 2.9 raised to the parenthesis 1 divided by 2. Okay, then times the whole thing in parentheses, 6.1 times 10 to the 3rd, end parenthesis, raised to the parenthesis, then the negative, not the minus sign, but the negative on your calculator, negative 1/2, so 1 divided by 2. And so our K value then would be 0.021803. That's going to be the 2 sig figs. So we could write that as 0.022 or 2.2 times 10 to the -2. Either one is acceptable. Okay, either one of those values are acceptable.
So is it possible to take the inverse of K, the first equation, and then add it through, and then at the very end take the inverse of that entire equation?
Say that again.
So instead of taking the inverse of the second equation, K2, you take the inverse of the first equation. So it's 1 over 2.9. And then add it through, and once you get that value, you take the inverse of that value. And then to the square root and all of that.
I think what you're saying is yes. I don't understand why you would do that, but I think that it would work. So you're basically taking it the inverse twice. You're basically solving for this reaction backwards and then taking the inverse of it.
Yes, but if that's the first thing that my mind goes to.
Okay, so that's called dyslexia. No, as long as you can handle it. Okay. Again, I don't care how you solve these problems as long as it's right.
All right.
The rest of you, I would not encourage you to do that.
If it's any easier, I used 0.5 instead of the fraction 1/2.
You can do that too. Right?
Yeah.
Yep. Again, I don't care how you do it. That's just. Okay, everybody good? Okay, let's try another. So this says fluorine dissociates very slowly at low temperatures. So for example, when it dissociates, and again, this is a problem in the upper atmosphere, when the fluorine dissociates, it creates atomic fluorine. Now remember, it has an unpaired electron on it, right? It has 7 valence electrons. So it has an unpaired electron and it makes it very, very reactive. So the value of Kp at -5 degrees Celsius is 6.4 times 10 to the -8. I want to know, what is the value of Kc? So Kaylee, what equation, concept, idea, how am I going to go about solving this?
You're going to use the equation that has Kp equals Kc, and then RT.
And remember, it's that quantity raised to del N.
Yeah, and then you'll just rearrange it to find Kc.
Okay. Kp was given to us. What's the value of R? We have two values of R that you're supposed to know, right? We have a 0.082058 and an 8.3145.
Does KP have a unit on it?
KP does not. KP doesn't have units. KC doesn't have units. We're going to deal with KAs, KBs, KSPs, KFs, KDs. None of them will have units. They're all equilibrium constants. What are the units of concentration for KC?
Are we thinking more molarity?
Yeah, molarity. What are the units of concentration for KP?
Is it ATM?
Atmospheres, right? So that's why we don't have to use units. It just saves us a hassle.
Oh, so 0.082058.
Right. And so I didn't write the units, but you really should learn these numbers in units, right? So this is atmosphere liter per Kelvin per mole. And this is in joules per Kelvin per mole. So again, not only knowing the numbers, but knowing their units are going to help you choose which one you need. Well, we know that KP is in atmospheres, so we're going to have to use that one. Now, I know this is strange, and especially if you've ever had me before, I'm going to ignore the units. The only reason I'm ignoring the units is they're not going to work out because we've already ignored the units here. Okay, so I'm going to put that. What's the temperature then? What is the
-5 plus 273.15.
Exactly right. So the temperature has to be in the absolute scale. So it's going to be -5 plus our 273.15, which is going to give us Kelvin. And so that is going to give us a value of 268.15. And this is to 1 sig fig, basically. I should change that. No, I take that back. This is the 3 sig figs, right? So if the decimal point is there, it's to here. So this is a 268.15. And again, I'm going to ignore the units. Okay, now, what about this del N? What does del N equal?
That would be the change in moles on both sides of the equation in terms of gas.
Exactly. That last part that you said is the really important part. It's the change in moles of gas. So if there's aqueous species there, liquids, solids, you're going to ignore them, and it's only going to be the ones that have the gas, right? So there's a gas, there's a gas. So it's products minus reactants. So there's 1 mole of gaseous products, and we're going to subtract from that the 1/2 mole of gaseous reactants. And so we have a 1/2, a positive 1/2. So this is just to the 1/2. Plug that into your calculator, and you're going to get a value then of 1.364 times 10 to the -8. This is just 2 sig figs, so this is going to be 2 sig figs. So it's going to be 1.4 times 10 to the -8. Okay, so that's our KC from KP. Any questions on that guy?
Do we always look at the coefficients as the go-to?
For del N?
Yeah.
Yeah, right. It's the number, del N is literally the number of product gas molecules. So in this case, there is only one product, but if there was more than one product and they were both gases, you'd have to add up those coefficients. That would be the number of moles of product gas. Then you're going to subtract from that the total moles of product reactant gas. So again, in this case, there's only one, but if there was 2 or 5 reactants and they were all gaseous, you'd have to add up all of those coefficients, again, just for the gaseous species. Okay. Okay, any questions about that? Okay, part B says this reaction can take place in the upper atmosphere in which fluorine molecules absorbed on an ice crystal before dissociating. So that's this here. So the gas absorbs onto a solid ice crystal. It then produces that atomic fluorine, and it actually melts the ice because it's exothermic. Okay. So I want to know, what is the equilibrium constant expression for Kc and Kp for the following reaction? So what is the equilibrium constant expression for Kc? Hannah, what do you think?
It'd be the concentration of the fluorine gas to the raised to the first over the concentration of the fluoride ion half raised to the half.
Okay, this is fluorine. We would call it atomic fluorine.
Mm-hmm.
We'd actually call it atomic fluorine. This we would actually call fluorine or molecular fluorine. There is no fluoride here. Fluoride would indicate that it had gained that electron and was an ion. But otherwise, you are right. It's this here. Okay. Again, pure solids and liquids don't appear. Okay. Taylor, what about Kp? What's the expression for Kp?
For Kp, would it be the same thing?
No. Well, let me say yes and no.
Do you include the solids in it, the other?
What was the concentration for Kc? How do we give the concentrations of reactants and products for Kc?
Find the molarities.
Molarities, right? And that's what the square brackets represent.
Mm-hmm.
What do we give Kp in? The concentration, what units of concentration do we give Kp?
Oh, is it ATM?
That's atmospheres. Now, what's the variable for an atmosphere? Atmosphere is the unit. What's the variable for atmosphere?
Is it 760?
No, nope, those are conversions between, let's say, atmospheres and torr or atmospheres and millimeter mercury. I want to know what is the variable. The variable is a letter or a symbol that represents that value. So if atmospheres are the units, what is the variable?
Pressure.
And what letter or symbol do we use to represent pressure?
Is it just P?
P. Okay, so now let me ask again, what is the equilibrium constant expression for Kp?
Oh, capital P of F.
Right, we're going to put sub F here just to say that, hey, that's the partial pressure of atomic fluorine. Okay.
Times capital P of, oh wait, no, divided by capital P of F2 raised to the power of 1/2.
Exactly, right? Just looks like that. So they're very similar, except that these are given in molar concentrations and these are given in atmospheres. Again, this is why we don't include the units, because we already know what the units of the concentration are going to be by what we put here. So Kc's always represent the molarities. And if there's nothing here and it just says K, we automatically assume it's the molarities. Most of what we do, when we do the Kas, the Kbs, the Ksps, the Kfs, and the Kds, they'll all be in terms of molarity. Only Kp is in terms of atmospheres. Okay? Okay, so next, given that the same value of Kp at -5 that we had up here for this reaction, now for this reaction, I want to know what the value of Kc is. So what is Kc? Given that Kp is this, what's Kc? Jada, what do you think?
Wouldn't it be the same thing? Because if Kc is equal to Kp, like for some instances.
Okay, so we're still using this equation here. Kp is still the 6.4 times 10 to the negative 8. R is always going to be that 0.08. The temperature was the same. What about del N? Was del N the same for this reaction as it was for this one?
Yeah.
Right. Again, remember, it's just the gas, the change in the moles of gas. This is a liquid. We don't care about it. This is a solid. We don't care about it. All we care about are the gases. So again, it's going to be 1 mole of product gas minus 1/2 mole of reactant gas, which again is going to be 1/2, which is exactly what we got there. So it's going to be the exact same value that we calculated earlier. Any questions about that? Okay, let's try another. So it said, would any of the following reactions go almost completely to products at equilibrium? So Leah, is this reaction going to go completely to products? What would you predict? What's going to happen at
Wait, what do
equilibrium?
you mean completely to products? Like it's all going to transfer over? Wait.
Yeah, so when it reaches equilibrium, tell me, what can you tell me about the concentrations of reactants and products when this reaction reaches equilibrium?
Okay. Well, they're going to be equal to each other, right? Like,
No, not
okay,
in this case.
let me think real quick.
What tells you about the extent of reaction? You're going to hear this term again, extent of reaction. It just basically means how much did it go to product, right?
Like,
so is this going to have a high extent?
completely transferred over, just broke apart?
No, we're talking about the concentrations of reactants and products at equilibrium.
Okay.
What tells us?
Is it the coefficients that there's only
No, coefficients mean absolutely nothing.
Okay, then I don't know. I'm grasping.
Caitlin, can you help her?
You have to look at the K value for.
Okay, so here's my K value. What's that tell me?
If it is in the thousands, then it would go to products, and if it's in the like tens of thousands, it would go to the reactants, and anywhere between, they would be like mostly equal at equilibrium. Both sides.
Okay, I'm going to go over that again. There's a bit of a mishap there. Can you tell me, is this going to be mainly reactants, mainly products, or considerable amount of both?
Mainly reactants.
That's right. Okay, so when it is 1/1000th or less, it mainly is going to remain in reactants. So this is going to mainly be reactants in the end. If this value is greater than 1,000, then it's mainly products. If this value is between 1/1000th and 1,000, so 10 to the minus 3 to 10 to the 3, we're going to have substantial amounts of both reactants and products at equilibrium. So in this particular case, since K is so small, there's going to barely be any products formed, and we're going to be mainly left with the original reactants. Okay? So Lee, what about this one?
Well, that one's very large.
Okay.
So because it's, wouldn't it almost maybe be complete? Or like it'd go.
always think of this,
Mm-hmm.
right? So if I have a lot of products and very little reactants, is this going to be big or small?
It's going to be big.
And then if I have almost no products, but I have a lot of reactants, is this number going to be big or small?
Small.
Yeah, right. So in this case, it's really big, really, really big. So that means we're basically going to end up with products and there's going to be almost no reactants left over by the time this thing reaches equilibrium.
Okay. I see how you're viewing it. I didn't get that before. Okay.
Okay. Does everybody get it?